Hi, everyone. I'd like to start by thanking the organizers for giving me this opportunity. So I'll be talking about piezoelectric route towards quantum transduction and some of the efficiency challenges inherent in this. So before I begin, just a brief overview of my research group. So at Bristol, we are primarily interested in looking at problems at the intersection between RF MEMS and integrated photonics. So in this talk, I'll primarily focus on taking ideas from RF MEMS and applying them to integrated photonics. But I just want to emphasize that we have significant activities going in the other way. That is in the development of and taking ideas from integrated photonics and using them to rethink RF systems from the ground up. Now, the key insight with all this platform development is that these platforms are only as interesting and useful as the quantum systems that one can functionalize them with. And so we also have some research efforts to try and bring a variety of interesting quantum systems, in particular spin systems, onto these platforms. So a broad umbrella overview of most of our research work is primarily on the development of hybrid quantum platforms. And before I begin the talk, I just want to take a brief digression and point out why is it that, at least in my view, most interesting quantum systems of the future will have some hybrid nature. Now, one can understand this in many different fashions. The ones that we have looked at in some detail is to try and understand the limits that classical computing systems impose on future photonic quantum computers. Now, photonics is unique and interesting in this way because the lifetime of a photonic qubit is ultimately tied to geometry, that is the length of the delay line that one can keep the photon circulating. And from a systems architecture perspective, this means that these systems will always be constrained by timing constraints. And that's because a significant number of classical calculations need to be performed before the next photon arrives, so to speak. So for the experts in the audience, this is basically calculating the byproduct operators and the commutation corrections. And keeping track of that basically takes time. So even with the state-of-the-art FPGA, one cannot do this arbitrarily fast. And so if you try to implement this with an FPGA and you calculate the maximum clock rate that one can implement this, you cannot exceed 200 megahertz, for example. Now, one way that one can work around these problems is to try and see if one can map the photon state from the qubit map the quantum state from the photon onto another long-lived quantum excitation, in this case, say a spin system. And this naturally makes the sort of path towards a hybrid quantum system. And in any hybrid quantum system, what is necessary is the need for sort of efficient quantum transducers that can take quantum states back and forth between these different physical domains. And that's the subject of this talk. So we'll be looking at a very specific class of quantum transducers that are taking states between the microwave frequency domain and the optical frequency domain. These quantum transducers are primarily been sort of developed in the context of trying to build distributed quantum systems around superconducting qubits. Now, so the canonical problem is if you have two superconducting qubits in two distant cryostats and you want to link them together in some way, then optics provides a natural approach. But it requires you to be able to efficiently transfer quantum states between the microwave and the optical domain. But it's important to keep in mind that the problem is a bit broader, that in addition to superconducting qubits, both spin qubits and trapped ion systems, for example, have transition frequencies in the 1 to 6 gigahertz regime. So the development of efficient quantum transducers is, in some sense, much more broadly applicable. The key question is why piezoelectric and why sort of this resonant acousto-optic approaches to building quantum transducers. So in principle, one can build quantum transducers using either electro-optics, magneto-optics, or acousto-optics. The main advantage I feel that acousto-optics has can be captured by looking at the sort of overlap integral. So any kind of interaction that you want to engineer between different fields can be parameterized by some kind of overlap integral and some coupling rate G, where the overlap integral is between the optical field and the RF field that you want to sort of overlap. Now, one of the main challenges that happens between performing this kind of microwave to optical signal transduction is the need to bridge this massive frequency range. So you have some RF signals that are at, say, in the 1 to 6 gigahertz range, and you have an optical signal at 200 terahertz. Now, this massive difference in frequency comes along with a massive difference in wavelength. So the RF signal, for example, has a wavelength of on the order of 10 centimeters, and the optical field has a wavelength on the order of microns. So it's very hard to engineer strong interactions between them. And that's the problem that Acoustic solves for you in some sense, that the same 2.4 gigahertz signal, if it's now converted into an acoustic wave, because of the much slower speed of sound, the acoustic wave has a wavelength on the order of 1.25 microns. And so you can now imagine that in the same wavelength scale cavity, you can engineer much stronger interactions between the acoustic and the optical fields. There's a second benefit that acoustic devices provide, which is that it's very easy to engineer or relatively straightforward to engineer high acoustic quality factors in the gigahertz frequency domain. And this underpins all RF filtering in modern smartphones. And so now, before we look at some of these systems in detail, it's good to look at the architecture of one of these sort of piezoelectric routes to quantum transduction. Canonically, one can construct a flowchart where the signal basically starts from, you start with the weak microwave signals originating from a quantum circuit. This weak microwave signal is first converted into some acoustic wave in a piezoelectric material. This acoustic wave is then injected into some optomechanical cavity. And the optomechanical cavity performs the conversion into the optical sideband, parameterized by some strong optical pump field. Now, it's important to keep in mind that this flowchart is constructed to point out that there are various steps involved in this construction, in this conversion process, each of which is characterized by some sort of parameters that parameterize the efficiency of each step. And for the overall transduction process to be efficient, all of these steps need to be equally efficient. And this is something that is a recurring challenge as we'll look at in this talk. And so the key idea here is that while it's easy to engineer a piezoelectric routes towards quantum transduction, the key challenge is to be able to do this with near unity efficiency, which is what almost all quantum protocols require. And there's a second issue with sort of minimizing the amount of added noise, but here we'll focus primarily on tackling efficiency. Now, while the architecture is relatively generic, the specific implementations of how you build a piezoelectric microwave to optical signal transducer depends primarily where you start with. So one can in principle start at one of the two extremes. So you can start with the best RF MEMS system. So in this case, these high overtone bulk acoustic wave resonators, and try and build an optical cavity around them so that you can engineer strong optomechanical interactions. So this is one approach which we'll discuss. The second approach, which is sort of more commonly pursued, is to start with the best optomechanical cavity geometries, in this case, these 1D nanobeam optomechanical crystals, and try and engineer efficient RF interfaces to them. Now, as you can imagine, both of these approaches have sort of complementary strengths and weaknesses, and sort of solving, and each of them have sort of hurdles that need to be overcome to build efficient quantum transducers. Second way that one can see this complementary nature towards these sort of bulk and integrated approaches towards quantum transduction is to realize that the transduction process needs to be carried out at cryogenic temperatures. And this presents opposite challenges to the two cases. Now, as we already said, this optomechanical interaction inside these systems is parameterized by a strong optical pump. So what matters is not the single photon coupling rate, but actually the product of the G0 and the number of steady state intracavity pump photons that are present inside the cavity. And here you see that the performance of most current transducers effectively falls into one of two domains. So you have the 1D optomechanical crystals or the nanobeam cavities that have very strong optomechanical interaction strengths with G0s on the order of megahertz or so. On the other hand, because they have these sort of photonic crystal-like structures have extremely large surface to volume ratios, at cryogenic temperatures inside a dilution fridge, you suffer from a lot of surface heating effects. So you can't really put a lot of photons inside the cavity. The bulk transducers, on the other hand, have the opposite problem. So here you can actually put a lot of optical power inside the cavity with very low surface heating. But on the other hand, the intrinsic optomechanical coupling strength is actually quite weak. And so you basically get transducers that fall either here or here, but the optimal transducers, which sort of maximize the product between the two, need to be sort of on the top right. And so the main goal is to take of this talk is to figure out how to sort of take devices that are sort of in these two extremes and sort of push them towards the top right. And just to reiterate again, the peak transduction efficiency inside any of these systems is actually the product of both the phonon injection efficiency. This is the efficiency with which you can load phonons into this mode from an applied RF signal, and the optomechanical cooperativity, which is basically a product of the strength of the optomechanical interaction inside these systems. And it's critical that both of these parameters be optimized simultaneously so that we can achieve this sort of top right-hand corner of these devices. And the best way to sort of look at this is to see that if you make a list of, if you tabulate the sort of current performance of all present day optomechanical transducers, sort of piezoelectric optomechanical transducers, you can see that the sort of peak coupling efficiency that one can achieve inside the system is very far away from unity. And if one asks the question, okay, what is the main reason that, or how do you bridge the gap between where the current performance is and sort of how do you get to sort of unity efficiency? It's important to understand that a piezoelectric optomechanical transducer in some sense has two subsystems to it. There is the RF to mechanical wave conversion, and then there is the optomechanical interaction. And these two subsystems are sort of have been traditionally sort of been separate. But the only way to achieve sort of high overall efficiency is to sort of co-design these two subsystems. To be more specific, if you take a bulk sort of RF MEMS like resonator, the RF to mechanical subsystem is actually optimal in the sense that because this underpins your modern cell phone technology. On the other hand, it's not obvious how to make very good or high G0 optical cavities around these structures, and that's something that we'll discuss. The integrated approaches have the opposite problem, that here because of the small mode volume optomechanical cavities, you get very strong optomechanical interactions. On the other hand, the challenge is in the RF domain. Like, how do you build efficient RF interfaces? How can you get all the RF phonons into these very small mode volume cavities? And so you can see that they have complementary benefits and challenges, and it's important to sort of and the only way that one can achieve truly high efficiency is to sort of co-design these two subsystems. So not only individually design the efficiencies of each, but to sort of figure out a way to sort of connect them with high efficiency. And that's the main theme of what we'll discuss. The first sort of kind of transducers are these HBAR-like devices. And so just to reiterate again, the key idea here is that these devices have some advantages, but they also have some disadvantages. And so in the first half, I'd like to discuss how we can take these devices from sort of this bottom half to make them a bit more optimal. So these HBAR or high overtone bulk acoustic wave resonators are basically variants of the FBAR resonators that underpin most RF filtering in modern smartphones, and they basically consist of a piezoelectric thin film of aluminum nitride sitting on some crystalline resonator, in this case silicon. So this is built in a MEMS process, so this device is suspended. So when you apply an RF signal across this stack, basically the piezoelectric film starts vibrating, and because the whole structure is suspended, it sort of shakes the whole cavity. Now, as mentioned, these structures have some real advantages from a sort of quantum transduction perspective, which is that first, the phonon injection efficiency is unity. That means that every RF photon that you put on the system can be converted into an acoustic phonon. Then more importantly, it's converted into an acoustic phonon in the exact mode that you want, which is quite important. The other major advantage is that these structures are a bit more macroscopic in nature. So because of their sort of relatively low surface to volume ratios, you get a lot lower intracavity heating effects, especially at cryogenic temperatures. Or the other way to think about this is that the optomechanical interaction in these structures can be significantly enhanced by sort of parametric pumping. So you can increase the intracavity pump photon numbers to get a large effective coupling rate. In this case, we build these devices through a standard MEMS foundry platform. And when you apply an RF signal across this, you basically excite the various thickness modes of this cavity. And these can be thought of as the longitudinal Fabry-Perot acoustic resonances of the structure. And you can see that you can easily measure these resonances all the way till 12 gigahertz, which is one of the main advantages of these RF MEMS-like approaches, is that it's very easy to get to high frequencies, and especially build transducers that work well at relatively high frequencies. In the MEMS process, unfortunately, the metal has a lot of surface roughness, and so our mechanical quality factors that we achieve in this platform are sort of significantly less than what the fundamental FQ product of the material is. Now, if you take the stack and you deposit a thin metal film on the backside, then you also convert this 1D acoustic cavity into a 1D optical cavity. So basically, there are these two mirrors, aluminum on the top and gold on the bottom, that basically make this a sort of 1D optical Fabry-Perot cavity. And you can see that once this structure starts shaking, basically its thickness effectively changes, and this gives you this optomechanical interaction. And one can measure this optomechanical interaction by sort of, you can see that when you look at the optomechanical response, the structure effectively behaves like a resonant acousto-optic modulator. So when you hit the thickness modes of this cavity, you basically get a strong transduction. There's some interesting things to note here, which is that the optomechanical interaction is primarily dominated by the so-called moving boundary effect, which means that the contribution is primarily due to the fact that the thickness of the whole cavity changes as you start exciting these various modes. And this one can see by looking at the response of the successive modes of the cavity. So you have even modes and odd modes inside the cavity, and you can see that you get an optomechanical interaction or the transduction only when you hit one of these even modes. And this happens because in the even modes, there is an effective thickness change of the cavity, as shown in the 1.2 and the 1.9. But in the 1.6 gigahertz or the odd mode, you basically don't get an net cavity change. Now, the key point here is also that one needs to be very careful in designing these transducers, because there's a lot of because these structures are relatively bulk, you get a lot of sort of intermodal coupling that happens. So in one of these low frequency modes, for example, you see a lot of fine structure that happens due to mode coupling and crosstalk. Now one can take these devices and also operate them at cryogenic temperatures. So we can take these structures and cool them in our cryostat, and we can measure transduction all the way to about 3.5 gigahertz at 10 Kelvin. Now, the key, so the structure has advantages in the sense that they are relatively easy to model and operate, but they also have some fundamental limitations in that the transduction efficiency inside these structures is relatively low, especially if you want to do quantum transduction. In particular, it's limited to around 10 to the minus 7 for the fundamental mode, and it actually drops for the higher order modes. But to understand how to improve these and to build actually quantum transducers around this architecture, it's important to understand why the efficiency is limited and what one can do about it. The main challenge is basically the fact that the optical cavity in these structures is designed around simple flat fabric ferrocavities with metal mirrors. And that has limitations in the Q factors that one can achieve. So this is less than 1,000. In our case, the surface roughness also limits the mechanical Q factor that is achieved. But most importantly, the optomechanical interaction in this case is parameterized by this moving boundary interaction, which is not phase matched. So you're not getting this strong interaction between light and sound that one can potentially achieve. So given these restrictions, but the structure still has fundamental advantages. As I said, the bulk approaches basically give you this nice advantage that you can impedance match these to 50 ohms, and you can get basically you can pump these cavities very efficiently. So if you construct a variant of these cavities, in principle, you can solve all of these issues. So these are the current devices that we are currently trying to build, which is that instead of working with the sort of traditional longitudinal or thickness modes of this cavity, if you instead work with shear modes, you can basically address all of these problems. So the nice advantage with shear modes is that they propagate much slower than the longitudinal modes, which allow you to bring the Brillouin frequency of these materials down. So in particular, the shear mode Brillouin resonance in glass is around 7.3 gigahertz. And if you can engineer the Brillouin scattering inside the structure, you can basically get a G naught that's an order of magnitude higher than what you can get with moving boundary contributions. The second advantage that shear modes allow you to do is basically they allow you to take the metals out of the cavity in some sense. So you can build a very high Q optical cavity using these sort of curved fiber cavities. So in contrast to a Q that was on the order of 500, now you can get a Q that is optical Q that's on the order of 50,000. So again, the goal is to basically get 7 orders of magnitude to reach sort of quantum transduction. The key challenge, and this is the one big unknown that we are hoping to find out, is what sort of mechanical quality factors can one achieve with these shear mode structures at low temperature. This has not been well explored, and it's not well known what sort of acoustic losses one can see. Longitudinal modes have been well studied at low temperatures at high frequencies, but not shear modes. But we are building our first set of devices, and we hope to answer this question very soon. But if we can put all of these together, and I refer you to this paper for the detailed calculations, we can show that quantum transduction can in principle be achieved in this platform. So in the last, so now I'd like to sort of switch to the other half, which is basically in the last 10 minutes or so, I'd like to discuss the other approach towards building quantum transducers, which is you start at the opposite domain. That is, you start with integrated structures that have very high optomechanical coupling strengths, and you want to figure out how do you build better RF interfaces to these structures. Now, one of the key questions to answer is that why is it difficult to build to inject phonons into these structures? And that becomes clear if you look at these modes carefully. So these modes are very tightly confined, which is what gives you this very high optomechanical coupling strength. But the transducer needs to solve two problems simultaneously. it needs to be able to simultaneously impedance match to 50 ohms. So assuming that your microwave signal is coming from a 50 ohm line, it needs to be impedance matched. But it also needs to do a mode matching problem. That is, it needs to take this mode and be able to effectively load this very tightly confined mode. And that turns out to be a major challenge. With optomechanical crystals, there is one further challenge, which is also important, which is that effectively, if you look at the symmetry of these breathing modes, so then most of the nanobeam, the high G0 modes of these cavities are these shear horizontal modes. And the shear horizontal modes don't quite have the right symmetry to be excited efficiently from focusing IDT structures. So these are the traditional transducers that people use. But there's a slight mode mismatch problem between the mode that a focusing IDT likes to generate and the mode of the nanobeam cavity, which sort of limits the overall efficiency, transduction efficiency that one can achieve inside these structures. So what can one do? In our research group, we are sort of taking a slightly different approach, which is to try and engineer mechanical supermodes around these nanobeam cavities. A supermode, the idea is sort of relatively straightforward. Instead of working with one mode that has very high optomechanical coupling strength, you instead try to hybridize this mode with relatively high optomechanical coupling strength with another mode that has the RF impedance properties. So, for example, this is a mode that can very efficiently couple. That you can design this the piezoelectric resonator to basically have an impedance that is close to 50 ohms. And in some sense, you get towards the best of both worlds. So now you have a sort of hybrid mode that between the say a contour mode resonator and an optomechanical resonator that allows you to simultaneously impedance match to 50 ohms because on the left side, and also simultaneously mode match to this nanobeam cavity, which has relatively high G0. And this idea works very well in theory. So, for example, for gallium arsenide, you can take by implementing the super mode and designing it properly, you can actually improve the overall transduction efficiency of these systems by almost 10 orders of magnitude. And the details are available in this paper. But the key idea is very simple, that instead of just dealing with one mode, you basically split the problem into two. You sort of hybridize the mode so that the left side of the mode, in some sense, addresses the impedance matching problem, and the right side attacks the mode matching problem. And so you can do both of those things simultaneously. So far, I've just discussed sort of architectural routes or sort of implementations of piezoelectric transducers. But ultimately, sort of related to this is also a materials problem. So there are many materials in which one could potentially try and build these kinds of transducers. And each of them have their own advantages and disadvantages. In our group, we have sort of primarily focused on building these devices in gallium arsenide. And the main motivation for that is because if you look at this transduction problem and analyze it in a bit more detail, it requires some kind of matching of rates between the electromechanical coupling and the optomechanical coupling. And it turns out that in sort of most scenarios, one is always limited by the achievable optomechanical coupling strength. So, or the sort of take-home message is that it's always good to work with a system that gives you very strong acousto-optic interactions. And gallium arsenide, as can be seen in this table, has some of the highest photoelastic coupling coefficients. In addition to this, gallium arsenide has some other advantages, like the 3.5. It's just a much more richer material in which you can add other materials more easily. The first things we did at Bristol was basically to sort of build these circuits a bit more systematically. So, I mean, essentially to build these circuits similar to what silicon photonics does. So as you can see, as these circuits start to scale and become more complex, it's good to have a sort of reliable fabrication process that can allow us to build bigger and bigger circuits. And sort of the best way that we know how to build large circuits is to sort of rely on some kind of foundry fabrication process. And so this is the first thing we did, was basically we tried to build a good passives process that was sort of derived from a silicon photonics-like process. And the main reason this can be done is because silicon and gallium arsenide have relatively similar refractive indices at 1550, which means that basically everything that you do with silicon you can implement in gallium arsenide, and provided that you release the substrate and sort of tether it properly, you can build circuits of arbitrary scale and complexity, some of which are shown here. But the whole reason for sort of building this process was not to show that you can build passives, but actually that you can build active devices inside this platform. And so the first thing that we wanted to do was to sort of figure out how to build resonant acousto-optic devices and try and implement this super mode ideas around these circuits. And so the test problem that we picked was to try and build sort of Lamb wave resonators around these micro-ring optical devices. And the reason to sort of pick this problem is because if you look at it, the high G0 mode of a nanobeam cavity is the shear horizontal mode, but you also get a shear horizontal mode inside a waveguide. So the waveguide also has a shear horizontal breathing mode, and you can see by symmetry that this shear horizontal breathing mode of a waveguide basically has the right symmetry to be well excited by a contour mode resonator. So if you figure out a way if you connect the breathing mode of a waveguide to this contour mode resonator, you can get very strong sort of phonon transport between the two, provided you do it right. And this is in some sense easier than trying to build a super mode around a sort of nanobeam cavity in some sense, just by symmetry. But there are a few key challenges. One is that in this kind of architecture, the piezoelectric coefficient of gallium arsenide being low means that the sort of piezoelectric resonator has to be a bit extended, which means that the mode becomes more and more delocalized and the G0 starts to drop. So in this case, the G0 goes from about 1 megahertz in these nanobeam cavity modes to only about 5 kilohertz, with sort of I mean, and the transduction efficiency scales with the square of G0. So that's something that is important to keep in mind. The other more important, the other thing, which is something that we are currently working on, is that you would like to be able to control all aspects of this mode hybridization. So it's not just, and that requires sort of a very precise control over nanofabrication to be able to sort of make two modes and sort of make them couple as you want. Even though, even with that said, we are already able to see some very encouraging results. So we can show that with these Lamb wave resonators, we are able to show microwave to optical signal transduction all the way till about 7.5 gigahertz. So you have these different contour modes, and every time you hit one of these resonances, you can basically show efficient transduction. The transduction efficiency in our experiments currently is limited. So it's about 1e minus 7 for the 2 gigahertz mode. But if that number sounds low, it's already about 5 orders of magnitude improvement over sort of existing results in gallium arsenide. And there's plenty of scope for improvement. The first is basically that the optical quality factor inside these resonators was lower than we anticipated. It's only about 20K. But the more important thing is that in these first experiments, we were very conservative with our tethering structure. So these suspended platforms, the acoustic loss is primarily dominated by acoustic wave leakage through the tethers. And so that limits our mechanical quality factors in these systems to only on the order of 300. But if you sort of are a bit more judicious about the way you can tether the structure, you can really push this number up. And this is something that we are investigating. The final point for achieving higher efficiency is something that I alluded to earlier, which is that you want to be able to sort of line up the mode of the contour mode resonator, which is this orange curve, with the right mode of the optomechanical of the mechanical of the optical cavity. And this is something that we are sort of doing a systematic investigation to try and identify what all of these modes correspond to, and which one of these is sort of optimal for engineering these super modes around. I think I'm almost out of time, so I'd like to conclude by pointing out that hopefully I've convinced you that that piezoelectric optomechanical systems present one of the most promising routes towards building quantum microwave to optical signal transducers. I also want to emphasize that sort of both the RF MEMS or the bulk acoustic wave approaches and the integrated sort of nanobeam optomechanical crystal approaches have the potential to achieve quantum transduction, provided the sort of system parameters be properly engineered. In particular, the optomechanical and the RF subsystem be properly co-designed. That's the main goal of what I wanted to convey today. I would like to end by sort of thanking people in my research group who sort of led all this work. But I also want to thank people from NIST. So a lot of this work began when I was a postdoc at NIST, and over the years I've had many interesting discussions with the NIST folks on many of these ideas. Thank you, and I'm happy to answer any questions.